Okay, we are live.
Just a second. Yeah. Just so hello everyone. Today we are first of all welcome to the session by Consulting Analytics Club at IIT Guwahati. I am Sumit Prabhakar, the ML Research Head. I am joined by my fellow club head Subhash Kedia, the Project and Competition Head. So today we have a session by Pranav Durai, who has uh, one of the highest levels of experience I've ever heard in ML. Pranav is a research-oriented engineer with 6 years of more than 6 years of experience with AI in AI, deep learning, computer vision. He has worked on OpenCV, which is one of the most famous modules in Python. I would say. At present, he's a senior perceptron engineer at 10x, and as a part of the founding team. At 10x, he is responsible for the design and development of novel vision systems and for autonomous superhumanoids. As I talked about it earlier, previously he was a senior computer vision engineer at OpenCV, and he's also serving as a research fellow at Stanford University School of Medicine, where he leads the development of BIRAT, a sophisticated software for 3D preclinical biomedical image processing. Sorry for that. Pranav, if Subhashi, you have something to say? Pranav, if you could take over.
All right. So you guys can hear me loud and clear, right?
Yeah, you are audible.
Okay, perfect. All right. So good evening. First of all, thank you very much for the introduction as well as joining the session today on a weekend. Really glad that all of you want to learn something new. All right. So let me quickly share my screen. Um, just a second. So I think my screen should be visible right now. All right. So welcome to this talk on decoding convolutional neural networks using PyTorch. My name is Pranav Durai, and I am a senior perception engineer at 10x. I'm also a research fellow at Stanford University School of Medicine, Palo Alto, and a member of the CEF Computer Vision Foundation. All right. So let me go through the agenda that we have for today. We'll start with a quick introduction to deep learning, and we'll move on to the components of convolutional neural networks, specifically for computer vision. And also, we will, explore a couple of CNN design practices that I've kind of learned over these years, and I'd be more than happy to share that with you. And in the end, we'll do an end-to-end model training pipeline using PyTorch, of course, and we'll try to train a model from scratch. We'll write all of these submodules using PyTorch code, and we'll try to perform inference and check the results of the model. All right. So does that sound interesting? So you can probably, share your comments over here on the chat box, right? All right. So let me move forward. All right. So let's start with an introduction to deep learning. So this is a baby, and this is a newborn baby, and it's introduced into this environment for the first time, right? It does not know anything. It's not aware of what it can do. It just exists there and it's just trying to move in the environment for the first time, right? And the mother is actually the first person that teaches new things to the baby, right? For example, the mother points to the father and says that, hey, this is your father. And then the baby would be able to recognize the father for the first time, right? And as days pass by, the baby learns to crawl on its own on the floor, even though the parents did not explicitly teach the baby how to do that. But it learns to do that for the first time, right? And if you don't monitor your kid, this is something that might also happen if it starts to explore the environment much faster, right? Um, and this is also when the baby starts to take the first steps for the very first time. It starts to look at humans around it, and it tries to mimic those actions, but it's not really there yet, right? It probably needs some kind of external support before it starts, walking properly. And here you can see that the baby is able to take the first steps for the very first time. And I think it's one of the most precious moments for the parents themselves to see their child walk in 2 feet for the first time without any support, right? So now the question here is, how are humans capable of learning, right? So it turns out that the human brain is one of the most complex organs in the human body, and it has approximately 100 billion neurons, right? So you can see the connections that are here in the neurons itself, and it is one of the most complex organs in the human body, right? And this is the neuron or the nerve cell. And if you've probably taken a biology stream in your 11th and 12th grade, I think this diagram would give you a lot of throwback, right? So you have the nucleus, you have the cell body, you have the dendrite, you have the axon, and also the axon terminal, right? So these are the components of this neuron, right? And the question, what happens is there is an input stimuli that the neuron receives, and based on that, it decides whether to fire up that neuron or not, right? So that is when all of these complex connections are formed within the neuron itself, right? So you have multiple neurons over here. So now the question changes a little bit, right? So can you artificially design a brain, right? And it turns out you can. So the first idea of the perceptron, the first mathematical model of the perceptron, was first designed by Frank Rosenblatt in the year 1958, right? And this is probably close to 70 years ago, right? And you can see that this is the initial model of the perceptron that he proposed. You can see that there is weights over here. So x1 over here represents the weights, the input weights over here, right? The inputs and the weights, right? So you have w1, w2, w3, and w4 over here, x1, and you have multiple weights over here, the inputs and the weight, right? And you have a summation and bias over here, right? So you have the input weights and you sum it up and you add a bias term over here, right? And in the end, you have an activation function. Now, this activation function actually decides whether you would want to fire up that perceptron or not, or will that input stimuli pass through that perceptron or not. It's like a filtering mechanism that happens over here. And this turns out to be a sigmoid activation function, right? And then you have an output, right? Y cap over here. So now, do you notice the similarity, right? You have the nerve, you have the neuron cell over here, and also the perceptron, which look very similar, right? So, what exactly is deep learning, right? So, it is actually a subset of machine learning that utilizes neural networks with multiple layers to be able to learn complex patterns from the data that you give it as an input, right? And this is how you would, formally define deep learning, right? Now let's look at a couple of components of convolutional neural networks, which are mostly used for computer vision based tasks, right? So let's see. But before we move deeper into trying to understand the components of ACNN, it is important to understand what does a computer see, right? And what you see over here is an image, right? It's an image of the digit 8, right? And you can see that each of these components over here has a value, right? And the component over here, the individual fundamental component over here, are called pixels, right? So pixels, they come together to form images, right? And you can see that they vary in terms of the value over here, right? So you have 0, and then you also have somewhere close to 255, right? So it turns out that 0 represents the black pixel, or the most darkest pixel in the image, and 255, on the other hand, represents the whitest or brightest pixel in the image, right? And the same is shown over here as well without the pixel representation, right? You can just see the numbers, and you can see that this complete part is highlighted, which is the digit 8. And also you can see that the pattern follows very similarly over here, which is higher than 200 pixel value, right? So images appear as pixels, and they are digitally represented as two-dimensional matrices, right? And that is what you can see over here. And that is exactly how a computer interprets images, right? All right. So, what exactly is the purpose of a convolutional neural network, right? So, the purpose is actually split into two stages, right? So, you have the feature extraction component as well as the classification component. So, in feature extraction, what you do is that you have a lot of images, right? And the CNN tries to extract features from these images, and then tries to create a vector space or an embedding space that it uses internally for the learning process, right? And the second part is actually classification, right? So now that you have all of these features which you have previously extracted in the previous stage, you would use these features to classify, right? Let me give you a very simple example. Let's say that you are developing a CNN to classify images. So between cats and dogs, right? The classic example. So what you would have is that you would have two directories or two classes, and each class would represent one individual animal, right? So cat would be a class, and then dog would be another class, right? And for each of these classes, you would have multiple images within that class to represent that class, right? So a cat can be in multiple ways, right? So there are different species of cats, right? You have different variants of cats. The same holds true for dogs as well, right? So if you want to develop a robust CNN which would be able to classify between these two animals, then it only makes to have a lot of these images so that it's able to represent those classes better, right? So you would use those images from those classes for feature extraction, and then you would classify them based on the feature, right? So after training, if you forward pass an image of a cat, the network says, hey, this is a cat. And on the other hand, if you forward pass an image of a dog, the network says that, hey, this is a dog, right? So this is just an example to get you all started, but we'll probably talk more about how this entire pipeline works. But this is just kind of an example that I wanted to share. All right. So this is the purpose of a convolutional neural network. All right, so I'd like to first start with two-dimensional convolutions. And you can see that this is an input image, right? And also you have the kernel over here. And the kernel is actually a small matrix of weights which slides over 2D data, and it performs element-wise multiplication, right? So it'll give you a single output pixel for each of those operations, right? So you can see over here is that this single operation is one operation, single, single, single operation over here, right? And after the compute is over, you have one single output pixel for each of those computations, right? And you can see that the kernel is a small matrix of weights, right? And you can see that the kernel is moving on top of the 2D input data, which is nothing but the image itself. And the kernel has these values over here internally, right? And you perform element-wise multiplication on the 2D data that you have, right? And in the end, the resultant value is over here, right? The computed value after the convolution is being performed, you have the values over here, right? All right. So let's talk a little bit about padding because just knowing convolutions is not enough, right? So let's say that I would like to convert a 5 cross 5 feature matrix into a 3 cross 3 one, right? What would happen over here is that the edges would actually get trimmed off because of the size of the kernel, right? But ideally, we would want the size of the input to also be the output feature, right? You would want them to be equal, right? So, but how do you do that? So, what you can do is you can intelligently, add this zero padding around the border of the input image. Okay, so this is actually called zero padding, and you have a 0 pixel value over here, right? And once what happens is that now the original pixels are placed in the center and the padding is beyond the edge that you can see, right? And if you perform the same conv operation on this setup, you would get the same size of the input and the output feature to be very similar, right? And this is how you would tackle that using padding. All right. And this is striding, right? So the next part of convolution is actually striding, right? So if you saw that there is a movement of the conv kernel itself on the 2D input image, right? And if you would want to control that movement, you would do that using striding, right? So over here, what happens is that if I set a stride of 2, then what would happen is that it would skip 2 pixels for each stride that it makes, right? And what would happen due to that is that you would have a downsized feature, output feature, which is smaller than the input size, right? So if you have a requirement where the output feature map needs to be smaller than the input size, then the only idea is to skip some of these slide locations of the kernel itself, and then you would do that using striding, right? So I think you can clearly see over here on the illustration that you have a 5 cross 5 image or the 2D input image over here, and when you downsize it using a stride of 2, now you have a 2 cross 2 output feature map, right? And you can control that behavior using striding. Okay. So let's get a better visualization of this, right? So let's introduce striding and padding together, right? So over here, you can see that there is a 5 cross 5 input image. And you can see that the parameter that has been set are a stride of 1 and padding of 0, right? So it keeps moving every single skip location, right? No skips, single stride over here. And you can see that you have a resultant output feature map, which is 3 cross 3, right? Padding 0. Okay. So now what happens is that I have stride of 1 and padding 1, right? So now you can see that there is an introduction of this 0 pixel padding around the edge of the image, and the same stride of 1 has been used to perform the conv operation. And now you can see that the dimensionality has been kept similar, right? So untouched completely. So 5 cross 5 image, and then 5 cross 5 over here as well, just because we introduced padding, right? So this is a second example over here, which says stride of 2, right, and padding 0, right? So now you can see that it skips the conv operation for every 2 pixels, right? So then what happens is that you get a smaller output feature map, which has been reduced over here in terms of the dimensionality, right? And another example over here, stride of 2 and padding 1, you can see that the input image has been padded with 0 pixels around the input image, and you have stride of 2, which gives you a resultant of 3 cross 3 output feature map, right? So this is basically striding and padding for convolutions, right? All right. So now we just previously we just had a look at 2D images, right? So basically two-dimensional images which has a single channel, right? So what would happen if you would want to talk about RGB images, right? Now RGB is the color format or the color space that all of our devices use, right? The monitor that you're seeing this lecture on uses RGB. The phone that you use to text all of your friends uses RGB, and every image that you capture using the camera on your smartphone is RGB, right? So how do you want to how do you perform convolutions on multi channel images, right? So you can see that this is an RGB image, and you can also see that there are multiple channels for this image. You have the red channel, you have the green channel, and also the blue channel over here. And when you add or concatenate all of these channels together, you get this complete RGB image. All right. So let's see how to perform convolutions on multi-channel images. Right. All right. So you can see that since you have multiple channels, it only makes sense to have a collection of kernels, right? So you would have n input channels, which means you would have n kernels to perform convolutions on those n channels, right? So what would happen over here is that you have the R, G, and B channels over here, and each of the kernels of the filter, it slides over their respective input channels, right? So you can see over here that there is a kernel over here for the red channel, there is one over here for the green channel, and as well as a kernel over here for the blue channel, right? And you can see that it slides over its own channel. It does not interfere with the other channel, right? And you have a processed version of each over here in the end, right? So let's look at that. In the end, you have a computed matrix over here for each channel, right? So then what happens is that each of these per channel processed versions of these matrices are then summed together, right, to form one singular channel, right? So that is completely feature rich because it has extracted features from n channels that you have given it as an input, right? So you would sum it together, and then you would let it form one single channel in the end, all right? And here, what happens is that you would add or you would introduce a bias term to the output channel itself to produce the final output channel over here, right? So this is the final output channel. And now, not just convolutions, but there are other layers which make up a convolutional neural network, right? And these are nothing but pooling layers, right? And you can find pooling layers in terms of two types, right? You have max and then average pooling, all right? So you have max pooling over here. What would happen is that you have a 4 cross 4 feature, right? And you're doing a 2 cross 2 kernel over it, right? And for each of these components, it would pick the maximum value for max pooling, and then it would bring it as the output over here after the operation has been completed for max pooling. So over here it's 7, over here it's 3, over here it's 9, and over here is 3 again, right? And on the other hand, you can see that there is an average pooling method over here, right? So nothing but it would take the average of that specific component and pull it down over here. So these are max pooling and average pooling, right? But then how would you decide when to use max pooling and when to do, average pooling when you're trying to build all of these CNNs from scratch? Right? So it turns out that max pooling actually extracts the most salient features from the feature map. And this makes sense, right? Because it is actually picking up the maximum value for each of the pooling window that it performs in that specific conv operation, right? And this actually, helps with spatial invariant representation, right? And that is exactly how or when you would use max pooling, right? And on the other hand, you have average pooling over here, right? And what happens is that you pick the average of that specific pooling window, and then you would use that as an output, right? And this mainly helps to downsample your feature maps, and it assists with reducing spatial dimensionality, but also it helps you to preserve all of these information while also trying to reduce the dimensionality, spatial dimensionality, right? And this is how you would make that decision, um, when to use a max pooling layer, and on the other hand, when to use an average pooling layer in your CNN. Right? All right. So you also have activation functions, right? And initially, when we spoke about the perceptron itself, we saw a filtering mechanism in the end, which I said is an activation function, right? And now this activation function actually decides whether to fire up that neuron or that perceptron or not, to make that connection or not, right? And it turns out that over these years, there are a lot of activation functions that you can use in your CNN, right? So let me pick an example. I think initially we spoke about the cat versus dog problem, right? And in the end, um, we would want this CNN to say whether the input image is a cat or a dog, right? And it turns out that it is a binary classification problem, 0 or 1, cat or dog, right? So you would use a sigmoid activation function in the end for classification, because a sigmoid activation function gives a 0 or a 1 as an output, right? So then what you can do is map 1 to cat and then 0 to dog. And then based on the input image, if you get 1, it's a cat. And if you get 0, it's a dog, right? And on the other hand, if you said that the problem is changed or tweaked a little bit to support multiple animals, so let's say it's not just cats or dogs, but it can also do cats, dogs, tigers, lion, elephant, giraffe, and all of that. So now you have n classes, right? And it's not a binary classification problem anymore. And in fact, it's a multi-class classification problem. So over here, you would introduce a softmax activation function, right? Because what would happen is that in the end, for each class, you would get a probability, right? So if you forward pass an image of a cat, for cat, you would have a probability of more than 90%, right? 0.9. While for the other animals, it will be close to 0.1, 0.2, somewhere close to that. Right? So that's how you decide which activation function to use, right? And over here, I would actually suggest that after this lecture, if you Google up one of these activation function over here, each of these activation functions has a dedicated research paper which talks about the problem that they're trying to solve, and also how it solves it, and the mathematical intuition behind each of those activation functions, right? And it turns out that ReLU, or rectified linear unit, is actually the most common activation function that you use in CNNs, mainly because it's pretty simple in terms of compute, it's efficient, and also it helps you to mitigate the vanishing gradient problem, right? So this is that. All right. All right. So we spoke about feature extraction using convolutional layers, and then we also spoke about multi-dimensional convolutional layers to extract those features. And we also spoke about pooling layers, which will help you to reduce the spatial dimensionality of the features that you extract. And also on the screen, you can also see the activation functions, right? So stage one of the CNN is over. So you have performed feature extraction on the input images that you have given the model as an input. So it only makes sense to talk about the classification part, right? So, oops. Yeah, it only makes sense to talk about the classification part. So if you'd want to do classification in a convolutional neural network, you would introduce a component called fully connected layers, right? So you can see over here, there are input nodes, and then you also have output nodes over here, right? So what you can observe in this component in the fully connected layers is that every neuron from the previous layer over here is actually connected to the current layer, right? So you can see over here, this part is connected to this. Every single neuron over here in the input node over here, right, is connected to each of those output nodes, right? And it's very similar to the computation that I showed previously in the perceptron, where you have the input node, the weight, and also the bias term that gets added, and then it passes through the output node, right? And this actually helps you to perform that convolution, right? The classification part in the convolutional neural network, right? So if you add all of these layers and components together, this is how the architecture of a convolutional neural network looks like, right? So you have the input. So this is an image of a car over here, and you can see that there it is actually split into two stages, like what I previously spoke about. You have the feature learning part and you have the classification part, right? And you can see that there are multiple con blocks over here, right? So convolution one plus AReLU activation function. Then you have pooling over here to do some kind of spatial dimensionality reduction. And then also you have another block of convolution plus AReLU activation function. And then you also have a pooling to do a little bit of dimensionality reduction over here. And that makes sense, right? So you can see that the size of the blocks are reducing gradually as you move forward, right? And in the end, what happens is that you do a flattening, right? So what you would do is you have a lot of these features, but they are in n dimension, right? But you want to do that, you want to perform a conversion over here from n dimension to one dimension, right? You have a single feature vector, 1D feature vector after flattening, which then passes through the fully connected component, which we spoke about previously, right? And the feature learning part, right? The feature learning part happens in the fully connected layer over here, because each of those neurons are connected to every other neuron, right? And in the end, since there are multiple vehicles, it only makes sense to introduce a softmax activation function over here. And you can see that there are multiple classes which the dataset had initially. And this turns out to be a car as an input image, which means the probability output from the softmax activation function for a car would be very high compared to all the other classes over here, right? And this is how the visualization actually looks like internally. You can see that all of these neurons are getting fired up internally when an input image is passed through the entire CNN, right? So this is actually MNIST, so basically handwritten numbers that you can see over here as an input. And you can see that for each input, there is a different combination of neurons that fire up, right? And this was actually possible after training the model on all of these classes, right? So in this case, 0 is a class, 1 is a class, and on the other hand, 9 is a class. So all of these numbers are classes. And after you train the CNN, it learns a pattern of neurons that it needs to fire up. So after you train the model, you just pass a input image, an input image of any handwritten number or digit over here, and it would actually classify correctly in the end, right? So this is actually how the neurons fire up, right? All right. So let me talk a little bit about convolutional neural network design practices, which means what are the design practices that you would need to remember or keep in your mind when you're trying to develop a CNN or any deep learning model from scratch for the first time, right? So let's have a look at that. All right. So let's understand how to choose parameters for Con2D and other layers in your CNN, right? So the first one is actually the number of filters, right? And it turns out that a higher number of filters actually increases the network's computational cost, right? So what would happen is that you should start with a very small number of filters, and then you can gradually increase the number of filters, right? If you have images which look very similar to each other, right? So let's take an example of a cat and a tiger, right? So they both actually belong to the cat family, right? And you can see that, or you can at least assume that the features between these two images or these two classes would be very similar, right? So it becomes really hard for the network to understand or differentiate between these two classes, right? So in this kind of a use case, you would have to increase the number of filters so that it would be able to learn more complex features, right? Not just the global features, but more complex features. So it makes it more easier for the network to then classify between a cat and a tiger, right? But keep in mind, if you increase the number of filters, it also increases the number of, or not the number of, but it increases your computational cost, right? Which means you would need multiple GPUs or at least a GPU with more VRAM so that you can fit your model within that GPU, right? And the second thing is actually the kernel size, right? So how do you decide between a smaller kernel versus a large kernel, right? So smaller kernels actually capture local features, right, with less computational cost, right? Which means if imagine that this is an input image, right? If you have smaller features over here, then smaller kernels can actually help you do that, right? But what happens is that, let's say you have the same input image, but you have a very large feature over here, which covers up the entire image, right? So if you use a small kernel to capture that large feature, it won't work out, right? So you would need to increase the size of the kernel so that it's able to capture that really large feature, right? And if your image has both small and large features, right, you can have a combination of these kernels, right? And you can place them gradually in the network so that initially it learns local features, and then after that it learns global features, right? And you would be able to learn, your network would be able to learn both of those representations, right, in terms of both local and global features. But as a starting point, a 3x3 kernel is a good default to start with, right? And what about the other layers, right? So we also spoke about stride and padding, right? And I think someone also, posted a comment on the chat asking how to make that decision, right? So you have stride and padding, and typically for a stride parameter, a stride of 1 is the best way to start with, right? But on the other hand, larger strides can be used to reduce spatial dimensions, right? And this actually depends on the kind of images that you have in your data set, right? It's not something that someone can decide out of the box and say that, hey, this is the value that you punch in for strides, and this is the value that you punch in for padding, right? So it only makes sense to break down the problem that you're trying to solve and then choose a parameter that works best for that. And also padding, it's best to use the same padding, right, to get the same output feature map very similar to the input feature map, right? If you want it to match, then you keep it same, as in adding zeros in the edge of the image. But if you would want to do a little bit of spatial dimensionality reduction, please feel free to play around with padding, right? And this is how you would do that. But a lot of trial and error is necessary over here, because without trying to understand what combination works really well to extract that specific feature in your input image, it's really hard to make a decision as to this is the right striding value or this is the right padding value, right? So I think that makes sense. All right. So how do you optimize the number of layers and also the parameters that you have, right? So the first thing is actually network simplification, right? So if you notice that your training takes a very long time and it's very slow, and then your model overfits, so then what you would have to do is you should start by simplifying your network, right? Instead of having multiple blocks, multiple convolution blocks, it only makes sense to reduce the number of layers or filters in your CNN, right? And in my experience, at least, I've understood that not all problems require very deep networks, right? And when would you add layers, right? So if your model underfits, right? For example, if it's not able to classify your classes that you have as an input, then it means that it's underfitting, right? So then what you would have to do is increase the number of layers to capture more complex features, right? So only then it would be able to generalize across all of the classes that you initially have in your data set as an input for the model to learn, right? And over here, deeper networks, right? If you increase the size of the network by adding more layers, then you would have to give in more data also, right? It's not just that you have a very small data set with probably 10, 15 images for each class, but you have a really large model with multiple con blocks, then it will not work out, right? So you would need more data and regularization techniques over here, like dropout or batch normalization over here to prevent overfitting, right? So this is how you would control that behavior, right? And what is the approach to feature extraction, right? So the first thing is actually layer hierarchy, right? I think we spoke about how to fit all of these layers in the architecture to decide which layer comes at what point of the neural network, of the con layer, of the con model, right? So the layer hierarchy over here itself is important, right? So what you can do is that the early layers that you have in your neural network should be able to capture basic features like edges and textures in the image, right? And the deeper layers, as you go much deeper into the CNN itself, it should be able to capture more complex features, right? Because it's able to combine all of these features into singular representations, which would become more complex features, right? So initially, it should be able to capture basic features, and then in the end, it should be able to capture complex features. And to understand this, to visually look at it and understand or validate whether your CNN is able to do this or not, it only makes sense to visualize each of these layers, right? So what you can do is use GradCam or Matplotlib and Matplotlib to visualize each layer's activation, so that you can see that in that stage of the feature extraction part, what are the features that the model has extracted, right? And this will help you to kind of again derive the parameters that you wanted to use in terms of padding, striding, pooling, as well as all of those parameters, right? And of course, I think we spoke about pooling layers over here to reduce spatial dimensionality, right? So this would be the approach that you would have to follow for feature extraction. Right? And these are a couple of my tips from working in computer vision for all of these years. I have three tips over here. All right. So the first one is actually data augmentation. Right. We spoke about this part where there are very less number of images for each class. Right. So try to imagine this scenario. Right. So let's say there are two classes, class A and class B, and let's say class A has 10 images, and on the other hand, class B has 25 images, right? And this is directly a class imbalance over here, which means class B is overrepresented compared to class A, right? So what you can do over here is that to increase the number of samples in class A to be able to match class B, you can apply transformations, right? So you can add rotations along an angle theta. You can add translations like zoom in, zoom out, warping, and all of that. And there are actually two types of transformation, right? So there is photometric distortion as well as geometric distortions, right? For photometric, you can play around with brightness, contrast, exposure, sharpness, blurriness, and all of those photometric distortions to increase more number of um, samples for that class. And for geometric distortions, you can include or introduce all of these techniques, which include rotations, translations, warping, zooming, zoom out. All right. So all of those come under geometric translation or geometric distortion. Right. So data augmentation actually is a very powerful technique that you can use to increase the size of your data set, but also to to aid with generalization of your model, right? So it's not like your model should be able to only classify images that it has already seen from the data set, right? So what if I download a random image of a cat from Google Images and then forward pass that as an input to the CNN model, and it says it's a dog, right? So that makes no sense, right? So it only makes sense to add or to introduce all of these variations in the data set itself during training so that it learns more complex features and it's able to generalize, right? The second thing is actually the learning rate, right? So it's basically how much information the model learns at a period of time, over a period of time, right? So again, a classical example, right? What if I ask you to learn an entire chapter in linear algebra over a night and then write an exam the next day, right? um, let's say you would probably score 50 or 60%, right? But on the other hand, what if I gave you the same chapter to learn over a week, over an entire week, and then I ask you to learn each page and spend 1 hour for it over that week, right? And then again, I ask you to write that exam, you would probably, you know, he would probably get 80 or 90% in that test, right? So it's very similar over here, right? So it only makes sense to add a learning rate scheduler to the model itself during training, which would help it to adjust or to dynamically adjust the learning rate during training so that it helps the model to converge better in the end, right? So this is a really good tip for training a model using learning rate and a learning rate scheduler, right? And the last thing is experimentation, right? So the CNN architecture itself, the design, at least the design and then the training part, right? It involves a lot of trial and error, right? It's not just that you build one really good model and then um, it's not just that you would just build one model and then it would work for multiple use cases, right? Each use case would have a different combination of layers arranged in different positions so that it performs well for that specific use case. So my suggestion over here would be to start small, right? So yeah, so these are a couple of my tips
for design practices, specifically for convolutional neural networks. And the next part is actually the end-to-end model training pipeline using PyTorch. But before we start that, I would suggest that we take a 5 minutes break. So I think it's 7:08 right now. Let's come back at 7. Let's come back at 7:13. All right. So let's come back at 7:13, and we'll be able to talk more about the training part of the entire model using PyTorch. All right. I'll see you then.
Hello, Pranav. Hello.
Yes. Yeah, Tarun, I can hear you.
All right. So, have we already covered the questions? Hello.
I'll be taking the questions in the end. I think I already mentioned that to the
Okay.
presenter.
All right.
Yeah.
Understood. Understood.
Yeah. All right. So I think we'll continue with the session over here. And this would be the second part of the session where we try to understand how to do this entire end-to-end end-to-end model training pipeline using PyTorch, right? And we would actually be looking at this example um, as part of this talk. So we would be training a custom CMNN model on the MNIST dataset. And you can see that these are individual 2D images of handwritten digits that you can see over here, right? And we'll design and develop a CNN model from scratch to classify um, these handwritten digits over here. All right. So yeah. So what we will do is I'll share my screen. Just a second. So I have actually I have actually made a notebook that you can use and try to follow along with me. All right. So let me quickly share my screen and show you that. All right. So I think this screen should be visible, right? So just Google my name and you would find my GitHub, right? So it's Pranav Durai 10, right? Just go into the repositories over here and you'll find this first repository, which is this IIT PyTorch talk, right? So click on that, and then you can clone this repository into your local machine, right? So this actually has a notebook, right? So if you open this, there is an IP and PYNB notebook over here, right? So just download this or clone this repo into your local machine and let me know. I'll give you 5 minutes for this. All right. And there is also a link on the chat with the repository link, right, to the notebook. So let's give 5 minutes for that. Download it, clone the repo, and wait for me. All right. All right, we'll just wait for another minute over here before we start. But if you have already cloned the repository into your local machine, there are two things that you can do, right? So option one, if you have already set up a Conda environment on your local machine with PyTorch, then you can directly run Jupyter Lab on your local machine to run this notebook. And the second option is to use Google Colab, which I think most of you would use if you probably haven't set up CUDA on your local machine, or if you don't have PyTorch, then it only makes sense to go ahead with a Google Colab based implementation over here, right? So open a new tab, open Google Colab, all right, and after you have the all right, so let me quickly sign in and I'll show it to you. All right, so you would see something like this, where you could drag and drop the notebook, right? So you just say File and then Open Notebook, and then over here you can choose Upload, right? And in the Upload tab, you can directly drag and drop the notebook that you cloned as part of the repository, right? So let me bring that up over here. Yeah, so it's the file I've just dragged and dropped it in over here. Yeah, and yeah, so this is how the notebook would look like, right? So have all of you reached to this point to be able to see the notebook? Actually increase the size so that you'll be able to see it. So have you guys reached this point, the notebook, and then connected that to Google Colab? Have you reached this point? Okay. All right. So what you need to do is get a GPU accelerated runtime, because this notebook actually requires CUDA acceleration, right? And it turns out that if you haven't used Google Colab before, it actually offers free GPU runtime, right? And so I think the free GPU that you would have in Colab is an NVIDIA T4. So you change your runtime over here. So what you do is click on runtime, say change runtime type, and choose the T4 GPU over here. I think by default it would be set to CPU. Choose T4 GPU, all right, and click on save. All right, so now you can see that it says connect T4. All right, so click on that. So that now what will happen is that it'll allocate a runtime with that NVIDIA T4 GPU, and you could use that to train the model, right? So, all right. So, yeah. So when you see a tick mark over here, it means that the resources have been allocated for you with the compute units as well as the GPU that you asked for, the T4 GPU, right? So let's actually quickly run through this notebook. All right. So I'll keep this quick. All right. So you have the inputs initially over here, right, in terms of imports, right? So just your classic NumPy for your array manipulation, matplotlib over here for to show all of those visualizations that you would have to see, all right? And then Seaborn again is really good for diagrammatic representation or graphical representation of your data. You can also do a lot of visualization, right? And TQDM is used to display progress bars when a compute is processing something, right? And these are mainly your torch imports, right? So you have torch over here, the main library, PyTorch library, and then you have torch.nn is actually the neural network module from PyTorch, right? And then you have your functional type over here, which can include all of the layers, right? And then torch.optim actually gives you the optimizers that you would have to use in your training pipeline, right? And then you have Torch Vision, right? So Torch Vision actually is a subset of Torch itself, and it has support of preset data sets and models and transforms, right? So the data set that we would use for this specific training pipeline would be taken from Torch Vision itself. And also, Torch Vision supports a lot of pre-trained models, right? So let's say that you do not want to to you do not want to build a CNN from scratch, then you can directly import a pre-trained CNN model, which is already part of the repository in Torch Vision, and you can directly fine-tune it on custom data that you would have in your local machine to train that model, right? So in that way, Torch Vision is really good and powerful. And also transformations are nothing but your augmentations, which we spoke about initially, right? So that is that. And then Torch summary actually talks about, so once you have the model architecture, you can see layer-wise number of filters, number of parameters for each of those for each of those layers in the model. So Torch summary helps you in that, right? And you also have the utils, torch.utils, where we import the data loader. And the data loader is nothing but let's say, a component which can hold all of the input data that we have as an input to the model itself to train that specific model, right? So you can split them into multiple mini batches so that the model can train much faster if you don't have high-end hardware, right? So that's a data loader. And in the end, you also have the sklearn, scikit-learn metrics, from which we import confusion matrix, which I'll show you in the end. And it would be used to understand how well the model predicts the outputs based on the ground truth versus the output from the model, right? And we'll see a visualization for that also, right? So what you can do is click on this and click on the play icon over here to run that cell, or otherwise you can also click on press and hold Shift and Enter to run that cell, right? Shift and Enter would run that cell. So after it runs, you would get a tick mark over here, all right? So let's wait for that. All right, you can see a tick mark over here, and it took 11 seconds. So you can see that over here. All right, so now let's move on to define the CNN architecture that we want over here, right? So I'm trying to make the architecture over here very simple, because this itself is a very simple task, right? So you can see that I've defined a class over here, and then you have these lines of code over here, right? And let's look at the con blocks that we have, right? So you have a first convolutional layer over here, right? The input is a single input channel, and you have a grayscale image as an input, right? And you have 32 output channels as an output. And the kernel size that you would want to set over here is 3, right? So I think we spoke about a 3x3 kernel as the default value that we would have to use to start building a CNN from scratch, right? So I'm naming that as con1, right? And it's a con2D layer, which we import from the nn torch.nn module, right? And this is the syntax to do that, right? So then in con2, or the second convolutional layer, we will take the output from the first conv layer and pass it as an input to the second conv layer, right? So think of it like a daisy chaining mechanism, right? The output from the first component goes to the second component, and then the output from the second component goes to the third component, right? So imagine something like that. So you can see that the output from the previous layer was 32 channels. And it turns out that the input for the second layer is 32 channels over here. And then you would output 64 channels, right? And you can see that the spatial dimensionality is increasing, right? And you have the kernel size over here as 3, right? So same kernel size. And padding is just 1. We are not going really crazy over here, right? All right. So here, after the initial con blocks, I'm introducing a max pooling layer over here. So you would import it using the nn.maxpool2d from the nn module itself. And then you would do this 2x2 max pooling operation over here, right? So this is how you would introduce a max pooling layer in your network, right? And this is actually a dropout layer, okay? So now what happens is that, just a second. All right. So what happens over here is that you have a dropout layer, which means when the weights pass through this specific layer, 25% of those would be, dropped out, right? So this is just to, prevent overfitting, right? So you drop out a couple of these neurons, and then you continue to flow the rest of the neurons inside in terms of weights, right? So if you drop it out at some point, then it helps the model to converge better. And this also, I think we spoke about this previously, would help to prevent overfitting, right? And then you flatten it over here, right? You have a flattening layer, which would convert that into a single, dimensional 1D vector of features. And then this is how you would orchestrate that network, right? So for the classification part, for the fully connected layers, we have a dropout again, dropout 2, which we have mentioned previously, and then a fully connected layer over here, which would give you like a 128 number of outputs. It would take a 128 input and give you 10 output classes for the MNIST dataset, because there are 10 classes in MNIST, right? So this is that part. All right. So I think I have missed out a FC1 layer over here, which would act as the initial layer. So I'm adding that over here. Right. So this is much better. And I think if you're following along with me, just add this line of code over here. So this is your initial fully connected layer, which would take that 64 output channel as an input, right? And it would give you a 128 representation in the end, right? And you take that as an input, perform, and give you an output of 10 classes, right? So just add this line over here for the fully connected layers, FC1. And then you can run this, all right? And you would get a tick over here, all right? All right, so what would happen after that is that you have an orchestration over here, right? And this shows the sequence of layers that we would want to use in our CNN model itself, right? And in the next code snippet, there are 3 lines of code, right? So the first one is to actually check if you have CUDA enabled machine, right? If torch.cuda is available, you would use the torch .cuda method to access your CUDA accelerated GPU, right? Otherwise, it would just default to CPU, which would be much slower, right? I think someone has asked what is the full form of a GPU and what does it do, and another person also asked why is a GPU faster than a CPU, right? So a GPU is a graphical processing unit, and you actually use GPUs to accelerate a lot of these matrix multiplications, right? Higher number of matrix multiplications as well as higher dimensional matrix multiplication, right? So think of it like a CPU has 4 cores to do a task, and on the other hand, a GPU would probably have 1,000 cores to do that job. So just imagine how fast a GPU would be able to complete that computation compared to a CPU, right? So that is why we use a GPU to train all of these deep learning models. And in the end, over here in the second line over here, we define the CNN over here, right? And we send it to our device, which is the GPU, right? And using torch summary, we are looking at the summary of that model, right? And this is the architecture that we previously created using the definition of the CNN architecture, right? So, all right. So we are kind of at the end. So probably we'll wrap it up in 15 minutes. So you have data loaders over here. And I think what we spoke about is that data loaders help the model to get smaller batches of data, and it kind of helps it to forward pass smaller batches of these data into the model so that it keeps learning iteratively, right? So over here, I have introduced transformations, right? And we're converting into a tensor, right? And a tensor is nothing but a fundamental computing unit in deep learning, right? So we convert that into tensor using transformation, and then you normalize for a single channel, right? And then that is what the MNIST data set has. So we normalize it before training, right? And over here, as part of transformations, you can add multiple other transformations as well, like rotations, color jitter, the photometric and geometric distortions that we spoke about previously, right? So you can have a look at the documentation for transforms in Torch Vision and then play around with this. But for MNIST, it's not required, so I'm just keeping it plain simple, right? And what we're doing over here is that we're creating a trained data set and a test data set, right? So, and we are importing that from the datasets method in Torch Vision, and .mnist will directly download it to your local machine, right? And these are just the parameters, right? So the trained data set will be used for training. So it's true. I want to download it. So it's true. And what transformations I want to apply on that is these transformations, right? So you just pass that as an input over here. It's the same thing over here. Test, same thing. Store it over here in the root. And I do not want to use this for training. So it's false. And download true, transform, same thing, right? And this is how you would create that data loader, right? So call the data loader, pass the trained data set, and choose a batch size. And a batch size would have n number of images per batch, right? So you have 64 images for a single batch. And you'd also want to shuffle it, right? So that you add some kind of randomness in your data. And then in the test loader, it's the same thing, but you would want to not use shuffle. Right? So let's run this as well. Yeah, so the downloads have completed, and also the train and the test loader have been created. Right. So this is just a small code snippet to iterate through the data loader that we created and see a visualization of the images. Right. So if you run this cell over here for data visualization, just a couple of simple lines of code using matplotlib to show you the grid of images in the MNIST dataset, right? And this is the last part, which is the training loop, right? So we're using a cross entropy loss function over here, and also the optimizer is an Adam optimizer, right? But in the interest of time, I would not be going much deeper into the criterion on the optimizer, but this is something that you can probably reach out to me, or you can also Google it and read relevant documentation, right? And we're training this model for 10 epochs, which means 10 iterations. And this is fairly a simple training pipeline. So 10 epochs itself would be much better to train this entire model, right? And you change the model into training mode, right? So it allows forward pass and updates of weights, right? And for each epoch in your number of epochs, you perform a forward pass through that entire set, right? So you have the image and the labels, right? And you send those image and labels to the device. So that is one single forward pass, right? And you update your optimizer, and then your outputs will be coming out of the model, right? As well as you update your loss, and then you do a backward propagation in your CNN, right? So you have a forward propagation and then the backward propagation component that happens. And then you have this optimizer step, which updates the optimizer. And then you have this running loss, which you update. And this is nothing but your TQDM progress bar, right? So if I run this, this will start training your model, right? So this is the first epoch over here, and it is training the model over here. So let's wait for that. So someone says, why is this so slow? But this is actually fast. So if you run this on a CPU, it would take much longer time. And yes, we can make this faster. So what you can do is you can increase the number of batch. The batch size can be increased. And also you can, also you would have to get a better GPU also, right? So this is actually a data center grade T4 GPU, which was not actually meant for training, but works really well for inference tasks. So you would probably look at training GPUs. So I actually prefer the RTX A1000 series. So the RTX A5000, the RTX A6000, right? They're really good training GPUs. And if you can really afford it, then NVIDIA A100 or H100 also gives you really good performance. But the funny part is, this is a very simple example, and you would not need very high-end GPUs to train a CNN for an MNIST classification task, right? So this is that. Yeah. And what we can do over here is I think it's going to complete over here. It's in the 9th epoch for me. All right, so my training has completed. Has yours completed as well? So you can probably let me know on the chat as well. So the next line is to just save the model. So you export a model.pth file, which has the best trained weights from this training iteration that we had over here, the training loop, right? And the last part is to just put the model into inference mode and then do one single forward pass and see the results, right? So over here, what you're doing is you load the last state over here, the state dictionary that we exported previously. And I think I've named it as last best model.pth, right? So you load that and you put the model into evaluation mode, right? I think previously for training, it is put into model.train, right? You change that into evaluation mode, right? So just one single forward pass happens and no backward propagation, right? So this is just to iterate through all the images in our test loader that we had over here, and then send it to the model as an input, right? You send that as an input to the model, and then you get the outputs, right? And you use that to kind of print a confusion matrix. So if we run this cell over here, you would get a confusion matrix. I'm zooming out a little bit so that you all can see it better, right? So how do we read a confusion matrix? So in this axis, we have the truth, the ground truth, right? You can see the legend over here which says truth, and over here on the bottom you can see that it says predicted, right? So these are actually the predicted inference outputs from the model, right? So how do you infer this? So 0 is the ground truth and 0 is what the model predicted, which means it's really good. So out of all the samples that we used, gave it as an input, 978 samples are good, right? It's the correct prediction. On the other hand, 1 for predicted and 1 ground truth, 1135 times, right? And you follow the same thing over here. So ideally, for a really good model, the diagonal in the confusion matrix should be of high value, right? And everything around that diagonal should be closer to 0, right? Or at least less than 10, right? And how do you infer that? So 0, but it has been predicted as 1 time, right? And let's look at a number which is very similar. So this 3 and 5 kind of look similar. So 4 times over here, those are false classifications over here, right? And then 4 as 9 5 times, right? So that's again a false positive over here. So this is how you would read a confusion matrix, right? And that brings us to the end of the end-to-end pipeline for training a CNN model from scratch. So in this example, I think we used the MNIST dataset to perform classification. But what I want you to do is take 24 hours from now, change the dataset from MNIST to any other image classification dataset which is already present within the Torch Vision library. Train the model, make some changes in the architecture and train this model, and print the results and post it on LinkedIn, tag me, and let me know how it went, right? I'd be more than happy to know if you actually followed along and if you got something useful out of this, right? But apart from that, I'll just quickly close this off. So I have a feedback form over here. So you can just use your smartphone to scan this, and it'll take you to a Google form, right? And just spend 1 minute letting me know how this went. If you liked it, let me know, and if you didn't like it, also let me know so that I can make some corrections when I go to my next guest lecture, right? So please feel free to reach out through the form, and I will reply to every response in the form, right? I'll send an email reply to every response that I get on the Google form. You can ask me doubts, you can give me feedback on the session, or also you can ask you can ask help from me if you have if you're working on any deep learning computer vision project and you need some assistance. Let me know. I'll be more than happy to guide you in the right direction, right? So I'm keeping this for 15 more seconds over here so that everyone scans it. All right, so if you want to reach out to me, you can Google my name. It's Pranav Durai. You can reach out to me on LinkedIn, GitHub, and Google Scholar. And I'd like to thank IIT Guwahati for arranging this with association with AI Planet. Thanks, Tarun, for the invite, and also thanks to the team at IIT Guwahati for making this happen. Be more than happy to spend this weekend with you guys today to teach all of this. And yeah, thank you very much. And yeah, see you soon. Stop sharing.
Hey, hi Pranav. Should we take few questions before the IIT Guwahati have their final words? We'll just take 2 or 3 questions.
Hello. Yeah.
Hello.
I think we can take questions. So
Sure. All right.
I think I answered most of the questions on the chat, but if there are any more questions, I'd be more than happy to answer.
Is this question already answered?
Let me check. Can I just input the pixel values into a model like XGBoost and get classification results? Yes, you can. So you can directly convert the dimensionality of your input image into a one-dimensional feature space, pass it through XGBoost, set your parameters for training, and then you can get classification based on that. So that is possible. Yeah. Okay, I think there is
All right.
another one which says, how do we decide how many convolutional layers? Okay, how do we decide how many convolutional layers to use in a model, right? So the best practice is actually to start with 2 or 3 convolution layers. But again, this actually depends on a lot of things, right? So it depends on the complexity of your problem statement. I think we spoke about the complexity of the problem, right? So if the images look very similar to each other, right, then you would need a very large CNN model, which means you would need multiple layers, right? But on the other hand, if it's just a simple task like MNIST classification, where the features are very different for each class, then you do not need a very complex model with multiple CNN layers. So that is how you would decide that. But the main criteria over here is to do a lot of trial and error in terms of experimentation to understand which one works best, right? So you would need to run all of those experiments and get the best possible result. And there was another one. What are pre-trained models? Like, how can they help us because our data will be different? Yes. So pre-trained models are actually trained on large data sets, right? So generic data sets. And one of the most generic data set is, let's say, ImageNet, right? It has a lot of these classes that the model will already look at it. So if you have custom data, So let's say that there are classes in the data set which the model has already seen, but you have custom data which kind of look similar to those classes, but have different features, right? So then you can directly use those pre-trained models and then fine tune them on your custom data, right? So which means the model already has pre-existing knowledge, and then in the end, it also can learn new data representation of the custom data that you have given it as an input, and it would work really well for that use case, right? So that is why you would use pre-trained models. Yeah, so I think this is the last question over here. So what is the benefit of CNN over classical models like XGBoost, right? So XGBoost is a very simple ML model that you can use for, mostly, let's say, CSV based data that you have, right? Numerical data, right? But on the other hand, a CNN is a deep learning model, right? So it captures and learns all of these complex features which the XGBoost model might not really converge to, right? So, and that is why the model itself is deep, right? Deep in terms of the number of layers it has, and also the number of connections that it has in between neurons. So a deep learning model like a CNN would be much better for more accurate and precise predictions. So that is how you would choose a CNN. And if it's a computer vision task, then it's a no-brainer to go with a CNN, right? So yeah, I think if you have more questions, like I said before, you can reach out to me through the form over here. I'll be more than happy to respond to each and every question that I receive, and also yeah, through social media, right? You can reach out to me over LinkedIn, GitHub, or also Google Scholar, and more than happy to answer.
Thank you, Pranav, for this amazing session introducing our viewers to, I would say, PyTorch as a course mainly focused on classical ML. Thank you for that. We will also be delving into computer vision in our next week of the course, so you guys can look up to that. Feel free to ping up Pranav on LinkedIn if you have any questions. Everything else is on the live chat, the GitHub repo, the feedback form, and also Pranav's LinkedIn. So uh, yeah, Subhash, if you have something.
Yeah, we will also be adding the link to the session and the GitHub link on our website, so you can access that.
Yeah. So I guess that's it for this session. Thank you everyone for joining in. Hope you all learned something.
All right, thank you very much. Have a great weekend. Bye.
Thank you. Bye.
Thank you.